Hello everyone. Welcome to section 8.3. We're going to talk about equivalence relations in this section. In the previous section 8.2 we talked about a relation on a set A and we talked about these three properties. Well, if the relation has all three of these, then we define it as something very important. That thing is called an equivalence relation. So let A be a set and R be just a relation on A. We say R is an equivalence relation if and only if R is reflexive, R is symmetric, and R is transitive. It needs all three of those in order to be called an equivalence relation. So if a relation has all three of these, then it's a very important relation. It's so important we give it a specific name. Now, I just want to bring one definition back into the picture that we've touched on previously, and that is this modular arithmetic stuff. I'm going to say let m and n be integers, and d a positive integer. We say m is congruent to n modulo d, or some people just say mod d, if and only if d divides m minus n. What that means is, notation-wise, we write m is congruent to n mod d if and only if d divides m minus n. So we've seen this modular stuff before. Quick example of that would be, let's take 17, which is congruent to 2 mod 5. And that's because if we look at the number 17, it's equal to 3 times 5 plus 2. So this 2 is the remainder that's left over. We've seen this before when we did, m equals q times n plus r, our remainder. We called the remainder d. We called this the quotient q. So we looked at this divisor stuff a little bit before. Another example, 3 is congruent to 3 mod 5. Well, that's because when we look at the number 5, or I'm sorry, not 5. When we look at the number 3, it's equal to 0 times 5 plus 3. Right, so you can see where I'm picking up this number 3 by doing 0 times 5 plus 3. This is allowed to be 0 or negative, right? We want d to always be a positive integer. Right? A positive integer d. Let's do one more. Let's say 21 is congruent to the number 1, mod 20. All right, and that is because if we look at 21, that's equal to 1 times 20 plus 1. Right, if we look at it in the other light, in terms of division, 21 divided by 20 has a remainder 1. So this is what we call modular arithmetic, which just sort of it simplifies lots of processes in mathematics. Some of the examples, I'll use this a little bit to look at equivalence relations. So far we know that we'll call something an equivalence relation. Well, first of all, it's got to be a relation. And then second, it's got to meet all three of those criteria. It's got to be reflexive, it's got to be symmetric, and it has to be transitive. let's take a look at a specific example. I'm going to say let the set A equal 0, 1, 2, 3, and 4. And we'll define our relation R to be the relation 0, 0, 0, 4, 1, 1, 1, 3, 2, 2, 3, 1, 3, 3, 4, 0, and finally 4, 4. Again, that is to say, to build this relation in terms of its, A is a finite set. So our relation here, 0 relates to 0, 0 relates to 4, 1 relates to 1, 1 relates to 3, etc., etc., etc. And we want to see, now we already know R is a relation on A, right? We're defining the relation specifically. So we know R is a relation on A, but is it an equivalence relation on A? Well, we have to check those three properties to see if it is. Is R an equivalence relation on A? Well, we have to check. And one of the ways we can do that, if you remember with distinct, if you look at finite sets, you can use what's called a directed graph. Right? So here is the directed graph for the equivalence relation R on A. So we'll mark down what we have, 0, 1, 2, 3, and 4. Right? So here's 0. Here's, let's put 1 over here, because I see 1 and 3 and 3 and 1. So maybe I'll do 0, 4, 3, and 2. I'm gonna try and make this look pretty based on what I already see so far. If you just line them up all in a row, then you can just draw your arrows. But depends on where you put your dots, how pretty it'll look. Hopefully this doesn't look too terrible. So we'll take the first one. 0 is related to 0. Remember, that directed graph just tells you that 0 is related to itself. 0 is related to 4, so that means 0 is related to 4. 1 is related to 1, so I just move back. 1 is related to 3. 2 is related to 2, so it just loops on itself. 3 is related to 1. Good, good. 3 is also related to 3. 4 is related to 0. And 4 is related to 4. Oh, wait, let me draw that to the node, not to the number. And 4 is related to 4. Well, to see if this thing is an equivalence relation, we would need to first check and see, is it reflexive? Reflexive meaning for any element x, does x relate to x? Meaning, does each element relate back to itself? Well, yeah, 0 relates to 0, there's the loop. 4 relates to 4, 1 relates to 1, 3 relates to 3, and 2 relates to 2. There's 0, 0, there's 1, 1, there's 2, 2, there's 3, 3, there's 4, 4. So yes. But that doesn't mean it's an equivalence relation. That only means it's a relation that is reflexive. We still have two more properties to go. Is this symmetric? Well, let's see. The definition of being symmetric means that for any two elements, x and y, in the set A, if x relates to y, then y must relate to x. Right? So it has to be a forwards and backwards relationship. Well, we can see that 0 relates to 4, and we get the reverse 4 relates to 0. So that's symmetric. 1 relates to 3, and 3 relates to 1. So that's symmetric, and that's all we need, right? Those are the only two elements that jump between each other, and they do go both ways. Same thing, 1 and 3. Those are the only two elements that jump between each other, and they do go both ways. Notice I don't care about anything else. I don't care about 1 relates to 2 and 2 relates to 1. because 1 does not relate to 2. There's no reason for 2 to need to relate to 1 either. So yes, this is symmetric, right? Namely because of these two, right? Since it goes one way, jumping between one element to another, it must jump back. Same thing here. Since it goes one way, it must jump back. So I need 0, 4 to match with 4, 0, which it does. And I need 1, 3 to match with 3, 1, which it does. Still not an equivalence relation yet. Can't say that yet because we haven't checked the third property. Right? Is it transitive? Transitive property means if you have x, y, and z, if x relates to y and y relates to z, can I make the direct jump from x to z? Well, not a single element in here goes from, x to y and then y to, it doesn't go anywhere. There is no z that the element jumps to, right? So I don't go from 0 to 4 and then from 4 to 2, which means I don't have to look for 0 to 2. There's no reason. 0 goes to 4 and then we're done, right? It doesn't have a third element that it jumps to. So is it transitive? Trivial, right? We would say that that's trivial. There is no transitive property to really check for when the biggest jump we make is just between two elements at a given time. So yeah, it is transitive. We won't say no, it's not transitive because it failed. It didn't fail. So yeah, it fits the bill. It's transitive. So there's our final answer. Yes. Is R an equivalence relation on A? Yes. R is an equivalence relation on the set A. Again, a very desirable property to have. So next up, I want to give us a definition to kind of extend this. I'm actually going to, so we know this is an equivalence relation on A, which is good. I'm going to keep this example as a working example. But I do want to throw the next definition at you and then use that definition within the same example. And I'm not trying to be cheap. I'm just trying to extend what we already have. So I'm going to start with this definition. I'm going to say let R be an equivalence relation on A, which in this case it is. But this works for any general relation in any general set. It is what this definition is good for. For each element, I'll use a lowercase a in capital A, our set. The equivalence class of A, sometimes we denote this for each element A in A, the equivalence class of A, which we denote, or at least the book uses this brackets A. And I know this can be confusing with like integral notation and the integer part function. Yeah, they stole the notation. Is set of all elements X in A such that X is related to A. So this builds a set where, that's our relation R. So this builds a set, and that set is what we call the equivalence class of A. Oh, sorry, this should be a lowercase a. Correct this. All right, we're talking about the element A in A. So this should be the equivalence class for this element, lowercase a. which gives us this notation, bracket A, is the set of all the other elements in the set capital A, such that all those other elements are actually related to this specific element A. Notice A is on the right-hand side here. Which other elements in the set relate to this specific element A in our set? So we would write the equivalence class of A is the set X, some other element in A, such that X is related to A. And X could be A itself, right? A can relate to A. We see it here, 0 relates to 0. So notice it builds a set, depending on what A you pick. And that's why I wanted to keep this working example that we already had, because it'll, do double duty for us. It'll let us talk about this same example so that we can find the equivalence class for each element in our set A. So this is our definition. It just boils down to which other elements in the set are related to the specific element I'm looking at. So let's reuse this exercise. First, we showed it was an equivalence relation. Now we can talk about find the equivalence class for each element in set A. What that means is we need to find the equivalence class for 0, the equivalence class for 1, the equivalence class for 2, the equivalence class for 3, and the equivalence class for 4. Right, and these are all going to be sets. So basically what we're asking is, which elements are related to 0 in this set? Well, 0 is related to 0 in this set. 0 is related to 0. What other elements are related to 0? 4 is related to 0 in this set. All right, so again, if you look at the definition, it's the set of all the elements X, such that X is related to this guy 0. 0 is related to this guy 0, and 4 is related to this guy 0. Don't pick this one, because this is the element X is 0 related to 4. That spits us in a different equivalence class. All right, but we will see some symmetry in these equivalence classes in a second. So let's find out which elements are related to the element 1. 1 is related to 1, so 1 is in that equivalence class. 3 is related to 1, so 3 is in that equivalence class. Let's see which elements are related to the element 2. 2 is related to 2, and that's it. Only the element 2 is related to 2. So I'm trying to pick up some random element that's related to this 2, and it just so happens it's itself. All right, so 2 is related to 2. These are some bad squiggles I got going here. Sloppy squiggles. So that's the set. That set only has one element. Let's see which elements are related to the element 3. 1 is related to 3. And 3 is related to 3. And that's it. The equivalence class for 4. Who is related to 4? Well, 0 is related to 4. And 4 is related to 4, the last one. And again, you'll notice some of these are the same. The equivalence class for 0 is the same thing as the equivalence class for 4. All right, those two sets are the same. And you'll also notice that the equivalence class for 1 is the same thing as the equivalence class for 3. So these two are not distinct. Right? They are not distinct equivalence classes. So if we want to look for distinct equivalence classes, without having to bother with this repetition of saying the same set twice, we would just take 0, 4, 1, 3, and 2. All right, we would take those 3 sets. Those are the distinct equivalence classes of A. All right, we just kind of omit the repetition. This is what we call a partition. So we use this word partition when we talk about distinct equivalence classes. It's just easier to say partition. This actually brings us to a really nice theory about partitions. And it goes a little something like this. Let R be an equivalence relation on set A. The distinct equivalence classes the relation R form a partition of A. So what that kind of just generally looks like, let's take this set A. That means that we can partition it into smaller, we'll say this is A1, A2. Well, let's just use subsets like A1, A2, A3, A4. That means the union of all these distinct equivalence classes is A. Right? And that's one way of kind of interpreting this theorem, is that the union, if we have all these subsets split apart and we bring them back together, if they're all distinct equivalence classes, then the union of all equivalence classes of A is equal to A. So that's one way of interpreting it. And the nice thing about this is they don't overlap, right? So their intersections are empty. And that defines a partition. So to say that the intersection of all, or say of any two distinct equivalence classes is empty, i.e. the empty set, right? The intersection of A1 and A2 is the empty set. but the union of A1, A2, A3, and A4 is exactly A. And so that's just a really nice way of defining what we call a partition. So let's look at another example. And I'm going to bring that modular arithmetic back. So let's take a look at the relationship. Let R be the relation of congruence mod 2 on the integer z, right? On the integers, right? Fancy z. What that means is, say that is for all m and n integers, m is related to n if and only if m is equal to n mod 2. So that is our congruence mod 2. And again, what this means is that 2 divides, I'll do this in a different color. Right? What this whole thing means is that 2 divides m minus n. So let's say we want to find the distinct equivalence classes of R. Is this a partition of Z? Is this a partition on the integers? Question. Well, let's take a look at, let's analyze this a little bit. How can we go about solving this and answering their question? Right? How do we find the distinct equivalence classes of R? Well, notice we're dealing with the integers. I'm just going to pick on a random element, say A. All right, A is some integer. For all these elements A in the integers Z, either A is equal to 2 times K, or A is equal to 2K plus 1. Every integer is either even or odd. We remember that way back when we talked about parity. That's called parity of integers. The parity of integers says either integers are in the evens or they're in the odds. And we'll say for some integer k. Right, so any integer can be written in either one of these two forms. So this means for A equal to 2k, we're going to have A is congruent to 0 mod 2. Why? Because it's even. If A is even, it's congruent to 0 mod 2. Right? There is 0 remainder left over. And for A equal to 2k plus 1, we will have A congruent to 1 mod 2. Again, this will be divisible by 2 with a 1 remainder. So it must be congruent to 1 mod 2. Think about the number, A is 11. That's congruent, 11 is congruent to 1 mod 2 because 2 times 5 is 10 and you still need plus 1. Whereas 10 is congruent to 0 mod 2, because 10 is just 5 times 2 plus 0, right? So it's congruent to 0. So that means we can look at these equivalence classes for 0 and for 1. What integers are in the equivalence class for 0? Well, that's going to be all the even numbers. Right, and there's an infinite number of them, so I'm doing ellipses, dot, 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 -4, -2, 0, 2, 4, dot, dot, dot. It just keeps going. All of these numbers will be congruent to 0 mod 2. So that's the equivalence class for 0. Which numbers are in the equivalence class for 1? Well, here maybe I'll bring some color into this. Right, there's 0. There's our equivalence class for 0. Any even number is going to be congruent to 0 mod 2. Any odd number is going to be congruent to 1 mod 2. There's no such thing as 2 mod 2 because you're back to being an even number, which is congruent to 0. All right, so this will be like -3, -1, +1, 3, etc., etc. So when we look at these two equivalence classes, they're distinct. Here's all the evens, there's all the odds. Does this form a partition of the integers? Yes, it does, because every integer is either even or odd. So yes, this is a partition on Z. I say this, specifically I mean the relation of congruence mod 2. So this mod 2, or arithmetic mod 2, does actually partition the integers. What it does is it partitions the integers into a set, even though it's an infinite set. I'm drawing some random set here, where it basically cuts them up and says, here's all your evens, and here's all your odds. The union of those two sets is the entirety of the integers, right? Every integer by the parity law is either even or odd. So if I union them, I get my whole set, and their intersection is empty. There is no integer that overlaps here. There's no integer that is both even and odd. Right? And that's why we specifically put 0 as an even integer. It can't be both. So equivalence relations, that's really all I wanted to do for equivalence relations, is just to cover the fact that an equivalence relations has to meet the 3 laws of reflexive, symmetric, and transitive. So if you see that word equivalence, make sure you're getting all 3 of those. And great examples using the modular congruence mod n, where n is some integer. So check all those out, and you'll see that when you look at all these cases where you look at modular arithmetic, it breaks them up into distinct sets. That's just the behavior of modular arithmetic, right? If you look at something mod, just going to pick a random number, look at something mod 7, it's either congruent to 0, 1, 2, 3, 4, 5, or 6. And then when you get back to 7, you're back at 0. When you go to 8, you're back at 1. When you go to 9, you're at 2, right? So it definitely breaks things up into distinct subsets. So again, if you have any questions, please let me know. Otherwise, I think we have one more section in 8.4 where we actually start really getting into the modular arithmetic. So this is a good connection. And then a couple sections in chapter 9. So stay happy, stay healthy, and I will see you in the next section.